Hello and welcome to the Cyber One YouTube channel. My name is Ray and this is part 3 of the Walking Robot series, Rate of Rotation. In the previous two parts, I first looked at the range of motions that each of the joints will need for a walking robot. In the second video, Fred talked about the torque required for each of the joints, giving us a list of maximum torque values. In this video, I'm going to talk about the speed of rotation. It's all well and fine for us to have plenty of power to lift a joint or rotate a joint, but it's not going to be much use to us if it takes 2 minutes to get that. So what we're looking for is power, and to get power we need speed as well as torque. So let's discuss the rates of rotation for each of the joints. The first thing we should look at is the gait, and that is a series of motions that form the walking action. For this, a good friend of mine, Alex Nader 40, recorded a video of himself walking on a treadmill. The video was recorded at 1080p at 30 frames per second. Now we can use the timings from the video to estimate the amount of rotation and the time it takes to complete that motion. Working from the video, the complete step cycle is 1.3 seconds or 1300 milliseconds. Since both legs are the same but offset by 50% of the cycle, we can treat them the same. Extrapolating the video out, it gives us 39 frames for the complete step cycle. Looking at the toe joint, observation shows that the toe rotates pitching up. Rather, it stays on the ground level, but relative to the foot, it pitches up as the foot is rotated around. It does a 45-degree rotation over about a 200 millisecond period. But as the foot is lifted from the ground, it pitches back down to zero position within 66 milliseconds. While it's pretty quick moving back down, it doesn't really need to go that fast. So we could get away with having it pitch down at the same rate it pitched up. We'll work out the speeds for both the pitch up and the pitch down, because when it comes to motorizing, it's going to end up being the same both ways. Pitch up 45 degrees divided by 0.2 seconds, or 200 milliseconds, works out at 225 degrees a second that it rotates. When we pitch down at 45 degrees, that's 0.066 seconds. And that works out at 681.8 degrees per second. We could get away with 225, but anything greater is going to be good. For our ankle, remember there are 3 separate joints in our ankle. Let's look at the X joint first. Observation of the ankle shows around 25 degrees of travel, with the front pitching up by 20 degrees just before the foot pitches down by 5 degrees at the end of the ankle travel. As the foot is lifted from the ground, the foot pitches back down to around 0 degree position in just 33 milliseconds. The foot pitches down by 5 degrees over another 33 milliseconds as it's placed back on the ground as the heel is rolled onto the ground. The pitch up occurs over the bulk of the foot contact with the ground, taking 600 milliseconds to travel to 25 degrees. The most rapid movement is the 20-degree pitch down over 33 milliseconds on a massive 606 degrees per second. The truth of the matter is the ankle does not need to be that fast, and we could get away with a speed down to 42 degrees per second. The Y ankle joint, when walking on level ground, appears to me to have no movement at all in this joint. However, when the ground is uneven, this axis will need to be very fast, approaching 600 degrees a second. The good news here is that the static torque on this joint is less than half what is required for the X-ankle joint, which means the same size motor can be used for about double the rate of the rotation. The ankle Z joint, observation of the video footage of the walking does not really help here. For the most part, the ankle Z joint only rotates while we are changing direction while walking. We can, however, make some assumptions, something that's very dangerous, mind you. If we assume a 45-degree rotation while the foot is on the ground during normal step time, we get approximately 600 milliseconds to complete the rotation, or 75 degrees per second. This does not take into account acceleration or deceleration of the joint. The knee joint is one of the hardest working joints in the leg when we're walking. Observation of the knee joint shows it is only bent during the time when it is not carrying any load. The knee is bending for approximately 234 milliseconds and then proceeds to straighten out for 333 milliseconds. For approximately 83 milliseconds, both knees are straight. At the point where the knee is at its most bent, the angle is between 65 and 70 degrees. Working on the greater bend of 70 degrees, we find the time from going from the straight bend is 234 milliseconds. That equates to around 299.145 degrees per second, or around 50 RPM. Note, this does not account for acceleration or deceleration of the rotation. For that, I would allow an additional 20%. The hip X joint, observation of the hip X axis shows the thigh moving through 35-degree range of motion, completing the full travel in 650 milliseconds. This equates to approximately 53.846 degrees per second, or around 9 RPM. The major difference here, however, is the hip joints alternately take the full robot load for around 650 milliseconds each step, while the hip is moving through a 35-degree arc. The hip Y joint. What observation I was able to make of this joint suggests that there's very little motion at all, if any, beyond backlash while walking is in progress. However, there will be rotation as the walking is started and possibly when stopping as well. When starting to walk, the centre of gravity for the robot needs to move in order to lift the foot off the ground. It does not, however, move the centre of gravity directly over or past the foot that remains on the ground. This results in the motion created by the hip motion to be cancelled out as the robot starts to tip, back at which time the hip Y-axis can return to the centre position. Since the hip joint separation is 210 millimeters, as given by Fred in the last video, we can assume the movement will be less than half that measurement, 105 millimeters. By adding up the known heights of the knee-hip length for the thigh of 450 mm, the knee-ankle length, tibia, of 400 mm, and the ankle height of 75 mm, we get a maximum height of 925 millimeters. Now we can use a right angle triangle, Pythagoras theorem, where the bottom is 105 and the side is 925 millimeters, and we can calculate out the angle of the lower corner. The difference between that corner and 90 degrees will give us the maximum amount of movement we are likely to see at the start of walking. That works out at 6.5 degrees. Since this is likely to take a quarter of a step cycle time, 320 milliseconds, we get 20 degrees of rotation per second. This may need to be quicker if we are recovering from a misstep. The hip joint. Observation of video footage does not really help here for us to see what's happening. We would need multiple views from various angles at the same time, something we don't have the equipment for. By observation of my own walking, I see approximately 15 to 20 degrees each side of the centre. That's a swing of 30 to 40 degrees for each half step. Based on that, we're looking at about 66.6 degrees per second. Note this does not account for the acceleration or deceleration of the rotation, and for that I'd allow an additional 20%. That'll do for this video. If you like the video, don't forget to click like. If you want to be notified when future videos come out, please remember to subscribe and ring that notification bell. If you'd like to help support the development of Walking Legs, then consider becoming a Patreon. There'll be a link in the description. And we will see you in the next video.